I'm going to look at an example now illustrating how to solve these circuits in using our Laplace transform methods by transforming the circuit directly into the S domain. So this is problem 4.4-4 from your text, and the circuit looks like this. We have a 1 Henry inductor, a 1 ohm resistor. There's a second loop here with another 1 Henry inductor, a 1 ohm resistor. So both these resistors are 1 ohm, 1 Henry, and we've got a voltage source, X of t, and that's in series with a 1 ohm resistor. And in this problem, we're interested in finding the currents in both of these meshes, so y1 of t and y2 of t, with these both assumed to flow in the clockwise direction. We're not given the initial conditions. Instead, we're told that the input voltage is 3 volts for all t less than 0, and then jumps to 6 volts at t equal to 0, and is 6 volts for all t greater than 0. We're interested in solving for y1 and y2 for all t greater than 0. That's our Laplace transform approach. We will use this information that x of t is equal to 3 to actually solve for the initial currents in the inductor. We only have inductors present, so we need to find the currents at t equal to 0 minus. So in this case, for t less than 0, I assume that the voltage source has been 3 volts forever, and so in that case, all the currents are constant, we have only DC currents and voltages present, and so the voltage across the inductor would be 0 because the currents are constant. So I can treat them as short circuits, and so in this case, the circuit reduces to just a 1 ohm resistor in series with 2 parallel resistances of 1 ohm. So I can find the total resistance would be 1 ohm plus 1 ohm in parallel with 1 ohm. That's 1.5 ohms of total resistance. And then so I can find for the current then from our voltage source, which is y1 of t, is just our voltage, 3 volts divided by the 1.5 ohms. So this is 2 amps. Okay. This is what the current is, again, for t less than 0. y2 of t, y1 of t is actually flowing into both these resistors, which are in parallel. They're equal resistances. So y2 of t, I could use current division, but y2 of t is just going to be 1/2 y1 of t. So that's 1 amp. So this now gives me actually my initial conditions for the current through this inductor, and then also the current through this second inductor. So now I can write my S domain equivalent in this manner. My voltage for t greater than 0, I can write that as 6 times u of t, so the corresponding Laplace transform voltage is 6 over s. I've got a 1 ohm impedance here. I've got the inductor, I'm going to use the series equivalent circuits for the inductor, which has the inductor in series with a voltage source. Minding the polarity here, this would be minus plus. Again, you want to pay particular attention to that, and then again for the inductor, the equivalent voltage here is L times I0. My L is 1 in this case. My Y1 of 0 minus is 2. So this voltage would be 2 in the S domain. The S domain equivalent of this 1 ohm resistor is just 1 ohm. Then I've got the second inductor, which was a 1 Henry inductor, so SL is 1, and then minus plus the initial current here of 1 amp times the inductance of 1 amp. So this is a 1 volt voltage source, and then finally I have the 1 ohm resistor, and again I model again my input voltage as 6 U of t, and then so X would be 6 over S. That's where this term came from. Again, what I'm interested in here are, write the currents down here at the bottom, are these two currents, Y1 and Y2. You can use actually any of the circuit analysis methods that you learned in a previous circuits course. I do have 3 voltage sources here, so I could use superposition, treating each source separately and come up with an equivalent impedance, and solve for Y1 and Y2 from that method, or use nodal analysis. I'm interested in the 2 currents Y1 and Y2 here, so I'm just going to use mesh analysis. In this first mesh, starting in the lower left hand corner and then adding all voltages as I go around the complete mesh, taking into account the polarities, I'm going to have minus 6 over S. Then here I've got an impedance, so the voltage would be that impedance times the current, 1 times Y1. And then similarly, I'll have the S impedance, S times Y1. This is just a voltage, so minus 2, taking into account the polarity. And then finally, here I'll have this 1 ohm resistor. Here I have this current difference. It would be 1 times Y1 minus Y2 is all equal to 0. In my second mesh, again, I'll start here in the lower left hand corner and go in this direction, in a clockwise direction. The current here flowing upward would be Y2 minus Y1. That's in my direction of travel, so Y2 minus Y1. And then I'll have plus SY2 minus 1, and then finally the 1 ohm resistor times Y2 gives me this equation. So now I've got the 2 equations and the 2 unknowns, Y1 and Y2. I'm going to skip the algebra and jump directly to the result. I encourage you to go through the algebra and prove this to yourself. But Y1 of S then becomes 4 over S minus 3 halves 1 over S plus 1 minus 1/2 over 1 over S plus 3. So this is in the partial fraction expanded form. And then for Y2 of S, we get 2 over S minus 3 halves 1 over S plus 1 plus 1/2 1 over S plus 3. And so finally I can go back into the time domain to find Y1 of t by taking the inverse Laplace transform of each of these terms. The 4 over S will become a 4 U of t. Actually, all these terms will have a U of t, so I'm just going to factor out the U of t. The second term, I have the minus 3 halves in front. 1 over S plus 1 transforms back into the time domain as e to the minus t u of t. And then similarly, 1 over s plus 3 would transform back as e to the minus 3t, and then all times u of t. So this is my expression for the current in the first mesh, y1 of t, y2 of t would be equal to 2, again factoring out a u of t, minus 3 halves e to the minus t plus 1 half e to the minus 3t all times u of t. So this would be the expression for the y2 current. Just a quick check here. We see that y1 actually settles down to 4 amps, and y2 settles down to 2 amps after these transient terms die away. Recall that our initial voltage was 6 volts across 1.5 amps, so that total current would be 6 divided by 1.5 or 4, and then we get y2, that 4 amp current would actually split between the 2 equal resistors, giving us 2. And this would be, a long time after our voltage switches from 3 to 6 volts, enough time so that these transients die out, and then so all of the currents are no longer changing, and that's because we have a constant voltage source in this case, and so my inductors would act like short circuits. I want to look at another way to actually solve this problem, which I prefer. It may seem like it's a little more work, but usually the circuits are slightly simpler, and then it has the advantage of it allows me to find the output for any input, and maybe more importantly it allows me to find the transfer function for the circuit. So here I break the circuit analysis down into 2 components. I'm going to first find the zero input solution. This is the portion of the solution that's just due to my initial conditions. Okay. 2 and S, and we have a 1 ohm resistor here. Remember, originally I had a voltage source here. Well, I'm going to deactivate that. I deactivate a voltage source by replacing it with a short circuit. Any current sources that I had in the original circuit I would actually replace with an open, but voltage sources I replace with a short. We have the 1 ohm resistor here, and then have an inductance here, voltage source here of 1 corresponding to the initial current through that inductor, and then a 1 ohm resistor here. Impedance of this inductor was S, because again that inductance was equal to 1 Henry as well. I can now find, I'm going to call this Y1 of 0, and I'll call this current Y2 of 0. These aren't the complete currents, these are the zero input currents. And again, using any circuit analysis method, I can solve for Y1 of 0, and I get 3 halves 1 over S plus 1 plus 1 half 1 over S plus 3, and Y2 of 0 is 3 halves 1 over S plus 1 minus 1 half 1 over S plus 3. And so back into the time domain, I can find, and these are the zero input currents, or the portion of the current that's just due to the initial conditions. 3 halves e to the minus t. If my initial conditions were 0, both of these currents would also be 0. I wouldn't have any zero input current if the state is also 0. So I have 3 halves e to the minus t plus 1 half e to the minus 3t all times u of t, and then y2 0 of t the inverse transform of this line is 3 halves e to the minus t from this first term minus 1/2 e to the minus 3t u of t the second term. Okay, these are not my total solutions. I still have to turn my attention to the zero state. The zero state circuit, I have all the initial condition sources set to 0 and include my actual voltage input, I'm calling X. And then with my initial conditions equal to 0, again, my equivalent circuit just reduces to the inductor, a 1 ohm resistor here, and then in the second inductor has an inductance of L, or of 1 Henry, so the impedance is just S, 1 ohm here, Y2, Y1, okay. And then now I can solve for, I'm going to leave X as a variable at this point and solve for Y1 in terms of X. If you do that, you get this result, S plus 2 over S squared plus 4S plus 3 times X, and then Y2 is 1 over S squared plus 4S plus 3 times X. I can plug in now, and I could have done this in the original circuit. Our X is actually equal to 6 over S, so I can plug that into my Y1 expression. I'll denote these Y1 of X because these are the components due to my actual input X. So I'll have 6 over S plus 2, and then in the denominator I'll have S times S squared plus 4S plus 3, which the second order term factors as S plus 1 times S plus 3. So I can do a partial fraction expansion and get 4 over S minus 3 over S plus 1 minus 1 over S plus 3. And then similarly for Y2 of X, I get multiplying it by 6 over S, I'll have just a 6 in the numerator, and then S over S squared plus 4S plus 3. This partial fraction expansion becomes 2 over S minus 3 over S plus 1 plus 1 over S plus 3. And so I get the corresponding now zero state solutions. Y1 of X would be, all of these terms are multiplied by U of T, so I'll have a 4 minus 3 e to the minus t minus e to the minus 3t all times U of T. And from Y2 of X, I'll have 2 U of T minus 3 e to the minus t plus e to the minus 3t U of T. And you should note that I'm not going to write out the expressions or do the algebraic combining, but note that Y1 of T, the complete response is Y1 of 0t plus Y1 of X of Y1 X of T, and similarly the complete Y2 expression is Y2 0 of T plus Y2 X of T. Okay. You might note also that this particular approach, I kind of had to solve the circuit twice. I didn't have as many sources might argue that the first approach is simpler. I just had one circuit to solve instead of two circuit problems to solve with the zero state and zero input solution. But using the second approach from the zero state circuit, I had an expression for y1 in terms of s. So I can easily find the corresponding system transfer function between the input and y1. That's y1 of s over x of s. And we found that actually to be equal to s plus 2 over s squared plus 4s plus 3. And then similarly, the transfer function between the input voltage source and the second mesh current is defined as that current over the input, and we found that to be 1 over s squared plus 4s plus 3. These transfer functions will turn out to be very useful for system analysis later on in determining various characteristics of the system by looking at the system transfer functions. Of course, these are the Laplace transforms of the corresponding impulse responses. So, in another approach would actually be to find h1 of t, the impulse response, for input x, and taking my output to be current y1 of t. And so I could find y1 of t by convolving h1 of t with x of t. Do the same for y2 of t. Convolve the input with a different impulse response, h2 of t, or work them in the Laplace domain. Again, for any input for which I can compute the Laplace transform, I can find y1, y2 directly without doing any circuit analysis now. So this approach allows me to solve the circuit, at least to come up with the zero state solution for a wide range of inputs without having to do any circuit analysis at all. That's kind of the beauty of this transfer function approach. I can easily find the output for other inputs. Once I've done some circuit analysis to find the system transfer function, then I no longer have to do any additional circuit analysis.